In the last lecture, we were discussing the definition of dimensionless groups as either dimensionless fluxes, ratio of convection and diffusion, or the ratio of two different kinds of diffusivity based upon the characteristic length, velocity scales and the diffusion coefficients. So, I defined the convective flux for you as the product of the normal velocity times the density of a quantity. Okay. That is the rate of transport across a surface per unit area per unit time. And the diffusive flux comes from the definition of the diffusion coefficient. The flux of a quantity across a surface per unit area per unit time is equal to minus of a diffusion coefficient times the difference in density divided by thickness. Defined in this way, the diffusion coefficient has to have dimensions of length square per unit time. Mass diffusion coefficient is just the mass diffusivity, has dimensions of length square per unit time. Thermal diffusion coefficient, when expressed in terms of difference in the energy density, is alpha, which is K by rho Cp. K is the thermal conductivity, Cp is the specific heat. This also has dimensions of length square per time. Momentum diffusion coefficient is the kinematic viscosity. Viscosity divided by density has dimensions of length square per unit time. So, these are the diffusion coefficients for mass, momentum and energy. What are the characteristic length and velocity scales? The length scale for flow through a conduit is the hydraulic radius. Okay. Hydraulic radius is area of cross section divided by the wetted perimeter. Okay. Cross sectional area perpendicular to the flow divided by the perimeter of that cross section. Okay. And the equivalent diameter, which is the length scale, is equal to 4 times the hydraulic radius. Average flux is total transfer rate divided by the surface area. Surface area is the perimeter times the length. Okay, it's equal to the perimeter times the total length. Okay, that is the surface area. Okay. So, the flux for flow within a conduit for mass, momentum or energy are defined as the total transfer rate divided by this surface area. And the characteristic velocity is just equal to the flow rate divided by the cross sectional area. Volumetric flow rate, volume per unit time divided by the area, which gives the average velocity. That is the characteristic velocity for flow in a conduit. Flow around a particle, the characteristic velocity is what is called the free stream velocity. That is, when you have a particle moving relative to the fluid, which is at rest far from the particle. Fluid close to the particle will move across, but fluid that is sufficiently far from the particle will be stationary. So, the difference between the particle velocity and the velocity of fluid far from the particle, that is the characteristic velocity, the free stream velocity. Hydraulic radius in this case is defined as volume divided by surface area, and the equivalent diameter is 6 times the hydraulic radius for a particle. The average flux for heat or mass is the total transfer rate divided by surface area. The Sherwood and Nusselt number are the average fluxes scaled by the right side of Fick's law and Fourier's law, with the length being the characteristic diameter. Peclet number is the ratio of convection and diffusion, velocity times length divided by the diffusion coefficient. Mass diffusion coefficient for Peclet number for mass transfer, heat thermal diffusion coefficient for Peclet number for heat transfer, and the Reynolds number is the ratio of convection and diffusion, velocity times the distance, the characteristic length divided by the momentum diffusion coefficient. The dimensionless fluxes for momentum transfer are defined slightly differently. For flow through a conduit, the friction factor is defined as the average stress divided by the kinetic energy per unit volume based upon the average velocity, the fanning friction factor, and that can be equivalently expressed in terms of the pressure difference that is divided to that is required to drive the flow divided by the length. Okay. Note that there is a difference between the fanning and Darcy friction factors. Fanning friction factor is based on average velocity divided by the kinetic energy per unit volume. Darcy friction factor is basically pressure difference by L divided by the kinetic energy per unit volume, and that is 4 times the fanning friction factor. Flow around objects, drag coefficient, the drag force divided by the projected area is an average pressure difference between the upstream and the downstream sides, that divided by the kinetic energy density or kinetic energy per unit volume. For flat plate, which has negligible area perpendicular to the flow, which does not block the flow, in that case the skin friction coefficient is defined as the average shear stress divided by the kinetic energy density. Average shear stress is the drag force divided by the tangential surface area. Okay, so that is the definition. So these dimensionless grooves can be classified as dimensionless fluxes, Nusselt or Sherwood number for heat and mass transfer, and the drag, friction and skin friction coefficients. Ratio of convection and diffusion, Beckley number, Reynolds number, and ratio of different kinds of diffusivities, the Prandtl, the Schmidt and the Lewis numbers. So these are the different kinds of dimensionless groups that are used in transport processes. Okay. There are other dimensionless groups also which are sometimes of interest. I will just go through some of these. Okay. So the independent dimensionless groups are either the ratio of convection and diffusion or the ratio of diffusivities, and the dependent dimensionless groups that we want to determine are the dimensionless fluxes, the dimensionless average mass or heat flux for mass and heat transfer, and the dimensionless average momentum flux, the friction factor, the drag coefficient, etc., for momentum transfer. Other dimensionless groups include, for example, the Froude number Vc square by g times the equivalent diameter, the square root of, okay, which is the ratio of inertia by gravitational forces. Okay. So this is a dimensionless group. You can verify that the numerator and the denominator have the same dimension. Numbers that involve surface tension, the Weber number, which is equal to the rho Vc square times the characteristic length divided by the surface tension gamma. Okay. This is basically inertia by surface tension. Or the capillary number, which is equal to mu Vc by surface tension, is equal to viscous by surface tension. And you can also have what is called the bond number, okay, which is defined as rho g L square by gamma, okay, which is the ratio of gravity by surface tension. Okay. So I can construct these dimensionless groups just based upon dimensional analysis and give a physical interpretation of them as the ratios of two different kinds of effects. Okay. Okay. So now we will look at some typical flow patterns in some further detail, and we will examine, we will describe the characteristic features of these flows. Okay. The simplest flow is actually the flow through a pipe. Okay. Okay. if you have a cylindrical pipe, okay, of diameter d, okay, moving with some average velocity v average. Okay. Now, even though it might seem a rather simple flow, there is actually the characteristics of the flow are rather complicated. Okay. There are two distinct regimes, okay, for a pipe flow. Okay. One is called what is called a laminar flow, okay, where basically you have smooth and straight streamlines, okay, okay, which are where the velocity does not fluctuate with time. Okay. So, if you apply a fixed pressure difference across, and after the initial transients have died down, you reach a steady flow where the velocity is independent of time at each location. The streamlines are straight, and diffusion across streamlines has to take place only due to transport across streamlines has to take place only due to diffusion, because there is no velocity in the cross stream direction. Okay. So, this is what is called a laminar flow. Okay. A second type of flow is what is called a turbulent flow. Okay. Okay. In a turbulent flow, even though the velocity is along the pipe axis on average, okay, the flow velocity on average is along the pipe axis. However, even when the pressure difference across the ends of the pipe is a constant, okay, you have fluctuations in velocity in all directions at each location. Okay. Okay. And these fluctuating parcels of fluid that are in correlated motion are what are called turbulent eddies. And this is what is called a turbulent flow. Okay. In a turbulent flow, the velocity at each point, if you measure it, fluctuates in time, and it is in all three directions. Okay. You could have fluctuations both along the flow direction as well as perpendicular to the flow direction. Okay. The average velocity perpendicular to the flow direction is in general non-zero. Okay. I am sorry, the instantaneous velocity in the perpendicular to the flow direction is in general non-zero, but the average of that instantaneous velocity is 0. So, if you average the velocity over some time period, it will be 0, but instantaneously that velocity is non-zero. So, you have fluid velocity in all three directions simultaneously, which are fluctuating in time. Okay. So, if I plot the velocity as a function of time, okay, the velocity in some direction, you will find that if it is in the flow direction, it fluctuates about some average value, and if it is in the other directions perpendicular to the flow, it will be fluctuating about 0. Okay. The average velocity is 0, but the instantaneous velocity is non-zero in the direction perpendicular to the flow. This happens even when the pressure difference that is applied is steady. Okay. There is no fluctuation in the pressure difference across the pipe. The laminar flow is observed for Reynolds number less than about 2100, and for Reynolds number greater than 2100, okay, greater than approximately 2100. Okay, it is not exactly 2100, but it is approximately 2100. For Reynolds number greater than approximately 2100, you have a turbulent flow. Okay. And the turbulent flow, it is flatter at the center, more plug like. The velocity profile at the center is flatter or more plug like, okay, and it is steeper at the walls, okay, steeper at the walls and flatter at the center in comparison to a laminar flow. And this transition takes place discontinuously or instantaneously when the Reynolds number crosses a threshold value. And the characteristics of these two velocity profiles are very different. In a laminar flow, as I said, the smooth line the streamlines are smooth and straight, and transport along the flow direction is due to convection due to the fluid velocity. Transport perpendicular to the flow direction, there is no convection because there is no velocity. Therefore, transport perpendicular to the flow direction has to take place due to diffusion. In a turbulent flow, the velocities are instantaneously fluctuating in all three directions, though on average they are in the flow direction. In this case, because you have parcels of fluid called eddies in correlated motion throughout the flow, okay, the transport in the cross stream direction also takes place due to turbulent eddies, due to the turbulent fluid velocity fluctuations. And in a turbulent flow, cross stream transport is primarily due to the turbulent eddies. Okay. The transport due to diffusion is actually small compared to the transport due to the turbulent due to the convection by turbulent eddies. And because of these, the characteristics of these flows are also very different. Okay. The Reynolds number in this case for completeness is defined as rho average velocity diameter divided by viscosity. Okay. That is the definition of the Reynolds number. So, the friction factor if you consider low Reynolds number, okay, you know that the wall shear stress, okay, just from dimensional analysis at low Reynolds number when inertia is not important, okay, when inertia is not important at low Reynolds number, the stress cannot depend upon the density. Okay. So, the stress can only depend upon the viscosity, the velocity and the characteristic length scale. And from dimensional analysis or from Newton's law of equation, you know that at low Reynolds number this tau w has to be proportional to, okay, mu times V average by d, okay, just from dimensional analysis. Okay. For a pipe flow when inertia is not important, the only parameters that can affect the wall shear stress are the viscosity, the velocity and the diameter, and based on dimensional analysis the wall shear stress has to be proportional to mu V average by d, okay, which means that the friction factor is equal to tau w by half rho V average square, okay, will be proportional to mu V average by d into 1 by half rho V average square. And you can cancel out one factor of the V average and you can see that this is proportional to mu by rho V average d, which is equal to 1 over the Reynolds number. So, the friction factor has to be proportional to 1 over Reynolds number in the limit of low Reynolds number. Since the velocity profile does not change for a laminar flow, the velocity profile does not change, it is the same as that for low Reynolds number. Okay. The maximum velocity changes, but the shape of the velocity profile does not change. Okay. And therefore, for the entire laminar flow, the friction factor has to be proportional to 1 over Reynolds number. We will see later that for a pipe flow, the friction factor is equal to 16 by the Reynolds number. Okay. And it turns out that for a channel flow it is equal to 12 divided by Reynolds number. Okay. So, in the limit of low Reynolds number, the friction factor has a unique value. Okay. Now, what about at high Reynolds number? Okay. At high Reynolds number you have a turbulent flow. The friction factor does of course depend upon the Reynolds number, but there is one other factor that it depends upon, okay, and that is what is called the wall roughness. Okay. So, if I have a pipe flow, okay, of diameter d, okay, and if I focus close to the wall of the pipe, okay, In general, every pipe wall will have some amount of roughness on it. Okay. You can have smooth pipes, you can have rough pipes and so on, okay. But any pipe wall will in general have some roughness on it, and that roughness will cause some fluid motion close to the walls. Okay. Okay. And because of this you have additional dissipation of energy. Okay. Because of this you will have additional dissipation of energy. And this roughness of the wall will have some characteristic length scale that is usually called as epsilon. Okay. So, therefore, the friction factor depends upon the Reynolds number and this parameter epsilon by the diameter. Okay. Where the roughness is large, you will have additional dissipation of energy due to the circulation close to the wall due to the roughness of the wall. Okay. And therefore, the friction factor could depend upon the Reynolds number as well as the scaled roughness. Since the roughness length scale is epsilon, the scaled roughness is just epsilon divided by the diameter. Okay. So, the friction factor depends upon these two parameters. And usually the friction factor versus Reynolds number is usually plotted on a log scale. Okay. This is called a Moody plot. Okay. Log of f versus log of Re. Okay. Let me be a little more specific here. Rather than writing log, I will write natural log, okay, in order to avoid confusion. Okay. So, throughout this course we will use natural log to the base e, okay, natural log to the base e, and not the logarithm to the base 10 or some other base, okay, in order to avoid confusion. If we write the log function, okay, we know that for laminar flow f is equal to 16 by Re, which implies that log of f is equal to log of 16 minus log of Re. Okay. So, therefore, you get a line with slope minus 1, okay, for the laminar profile. Okay. This log f is equal to a constant minus log Re. So, in log f versus log Re graph you have a slope of minus 1. Okay. This is for the laminar. Okay. Okay, for the laminar flow. Okay. Log f by log Re, this is 16 by Re. And then there is this transition that takes place at a Reynolds number of approximately 2100. And you have a transition to a turbulent flow. Okay. It turns out there is a discontinuous change in the friction factor at this point. For a smooth pipe, for epsilon is equal to 0, there is no roughness, you get a curve something like this, and then you get different curves as this roughness factor increases. Okay. This is, for example, epsilon is equal to 10 power minus 2 times d. Okay. Epsilon is equal to 10 power minus 1 times d, and so on. Okay. So, you get different curves depending upon the roughness. The point to note, the friction factor for the turbulent flow is higher than the extrapolation of the friction factor for the laminar flow at that same Reynolds number. Okay. At that same Reynolds number, there is a discontinuous increase in the friction factor when transition takes place, and the slope is also less negative, okay, after transition. Okay. Slope of minus 1 before transition, slope which is less than or rather which is greater than minus 1, which is less negative when after transition, and because of that the friction factor after transition is always higher than the friction factor in the laminar flow. That is because we have transport of momentum by turbulent eddies, which is a more efficient mechanism in comparison to the transport by diffusion in a laminar flow. Okay. Now, for laminar flow we have the correlation 16 by Re. We do not really have a similar correlation for turbulent flows. Okay. There are several approximate correlations. Okay. I will discuss only one of them, which is called the Kohlberg equation. For a turbulent flow. Okay. This is an approximate empirical correlation. Okay. It is not derived from some fundamental equations, but by fitting the data for turbulent flows. I should also note that this is a classical correlation. There have been several improved versions of this correlations over the years, and so if you are actually using this in order to predict the friction factor, it is preferable to use one of the newer correlations which has a better fit to the data. This correlation is useful because of its simplicity, and so I will just discuss that in this context. Okay. The Kohlberg correlation is written as 1 over square root of the friction factor, okay, is equal to natural logarithm of 1.25 by Reynolds number times square root of f, okay, plus epsilon by 3.7 d. Okay. Ln is the natural logarithm, okay, and I have a minus 1.737 a factor there, and that is because the right side, the argument of the log is usually less than 1. Epsilon by d is usually much less than 1, and I have a Reynolds number in the denominator. Okay. So, both of these are less than 1, and because of that 1 over root f will be a positive number. Okay. I should note that usually you will see the Kohlberg correlation written in log to the base 10, in which case this coefficient would be about minus 4. Okay. The coefficient would be about minus 4 if you write in terms of log to the base 10. Here I have used the natural logarithm, so I get this coefficient as minus 1.737. Okay. And this is an implicit equation for the friction factor. Okay. So, on the right side you can see I have 1 over Re root f. So, the friction factor appears on both the left and the right sides. Okay. So, you cannot explicitly solve this for the friction factor. Okay. You cannot explicitly solve this for the friction factor. Okay. However, this is an explicit equation for the velocity if the friction factor is given. Okay. I get that by just substituting the values of the friction factor, okay, into this equation. Okay. So, we know that F is equal to delta P by L 1 by 2 rho V average square. Okay. Okay, there is a negative sign here, okay, because the difference in pressure between the inlet and the outlet. This is the fanning friction factor. Okay. And I should also note that the expression I have written down is for the fanning friction factor. You will get a slightly different expression if you use the Darcy friction factor. Okay. So, here we are going to use the fanning friction factor throughout the discussion. Okay. So, if I substitute that along with the Reynolds number is equal to rho V average d by mu, okay, then this factor here of Re root f, okay, Re root f is equal to minus delta P by L, okay, the square root of 1 by root of 2 rho V average square to rho V average d by mu. Okay. And you can see that the V average cancels out between the Reynolds number and the friction factor. So, Re root f is only a function of the pressure difference. Okay. Re root f is only a function of the pressure difference. So, if I express this in terms of the pressure gradient and the velocity, okay, what I will get is an expression of that form V average root of 2 rho by d into delta P by L. Okay. Okay. I should strictly speaking use the magnitude of the pressure difference here, because the delta P is negative. Okay. So, this delta P is understood as being the magnitude. Okay. Okay. is equal to minus 1.737, okay, ln of, now this term here is independent of the flow velocity, okay, this term here is independent of the flow velocity, and therefore I get 1.77 mu, okay, after some simplification, by root of rho d cubed into delta p by L plus epsilon by 3.7 t. Okay. So, this is now an explicit function of the velocity. So, I can divide throughout by this prefactor, okay. I can divide throughout by this prefactor, and I will get an expression for the fluid velocity field. Okay. So, given a pressure difference, I can predict what is the average velocity, okay, using the Kohlberg correlation. For a given average velocity, I cannot predict because it is now an implicit function of the pressure. Okay. So, I cannot get pressure in terms of velocity explicitly, but I can get the velocity in terms of pressure explicitly. Okay. And the Reynolds number is equal to rho V average d by mu, okay, is equal to minus 1.228 root of rho d cubed delta p by L, okay, by mu ln of the same factor 1.77 mu by So, this is the explicit expression for the average velocity and for the Reynolds number as a function of the pressure difference. Okay. And you can easily verify that these factors, okay, these factors are actually dimensionless. Okay. These factors are actually dimensionless. Okay. So, you can verify that quite easily. So, you determine the friction factor relation to the Reynolds number either from the Kohlberg correlation or using these charts, okay, this Moody chart. Okay. This is called the Moody diagram. For the turbulent flow through a rough pipe, okay, for the turbulent flow through a rough pipe, or you just set epsilon equal to 0 for the turbulent flow through a smooth pipe. For a laminar flow, it is just equal to 16 by Re. Okay. So, this is the brief discussion on the characteristics of the flow through a pipe. The next lecture we will look at the flow past a flat plate which does not block the flow, and then proceed to flow around a particle, okay, a spherical particle. So, I will continue this in the next lecture. I will see you then.